Now we understand how to compute the electric field and electrostatic potential. So next problem is how to hold the electric charge in a container. Such a container of electric charge is called capacitor. And capacitor is usually conducting material that are not connected. Not connected. That's a very important. And holding these charges is the basic mechanism of holding this plus and minus charge is their attraction. And that is called Coulomb force. So Coulomb force allows us to save some charge. So when this conductor pair is connected, this net charge becomes a 0. And we begin with the neutrally charged pair. And if we connect them via a battery that let move electrons from this side to that side, and this battery works to increase the amount of net charge saved in each part of a capacitor. So we learn how to do that. So attractive force of positive and negatively charged particles is the source of containing electric charge. If we, the capacitor, this is a capacitor, and capacitor is called the charged if they have non-vanishing positive and negative charge. We assume that both of them were neutral in the beginning. Geometry of each capacitor determines the amount of charge saved inside the capacitor. And the amount of charge is written in the form in units of voltage. So that is called capacitance. You remember heat capacitance. Okay? SI unit of capacitance is farad, and this one is named after Michael Faraday. And that is just Coulomb per volt. You know the circuit unit, circuit element battery, the thick short line represent the negative, and the thin long line represent the positive terminal. For simplicity, we first consider a parallel plate capacitor. We remember if a plate is charged with sigma and the other one is charged with minus sigma, there is an electric field that is sigma over 2 epsilon 0, and outside the electric field is vanishing. Remember, the process of piling of charges, plus and minus, is called charging process. The reverse process is called discharging a capacitor. You will find if there is a charge Q and minus Q, if you increase the amount of charge from Q to Q plus delta Q, then the other side will reach minus Q minus delta Q. This process can be understood that there is additional charge plus delta Q and minus delta Q. this is a 0. Let me bring this guy to here. Then the final result is like that. If you integrate this from 0 charge to capital Q charge, you know how to compute the work done by the external force to increase the amount of charge. You will find the energy can be expressed in terms of the net charge and the capacitance. This is a very important point we have to learn in this class. Discharging process, opposite. Let us compute the capacitance. Capacitance C is defined by this. And let me consider the potential difference between the two plates. For example, if we have two parallel plates, sigma and minus sigma, and we know the electric field. What's that? Sigma over epsilon 0. And electric field is constant between the two plates. So what is the potential difference between them? Minus E, this one, this integral. And actually, in the case of constant electric field, E times a D is the potential difference between the two plates. And we know this is E is a sigma over epsilon 0 D. What is sigma? Sigma is charge per area. Replace this one. That means this is charge Q per epsilon 0 area D. We have reached the point that Q equals something times V. What should I do? Q equals epsilon 0 A V. Where is V? And where is D? D. QD. Okay. So looks similar. Q equals something multiplied by V. Aha. This is the capacitance of the parallel plate capacitor. This is a way how to compute the capacitance of a capacitor. Circuit. You have a capacitor at t equals 0, no charge. When you close the switch, electrons will flow along this direction to let it be negatively charged. Because of the conservation of charge, if minus Q has been moved to this plate, the other guy with the same amount plus Q will be charged on the left-hand side. Parallel plate capacitor, what we have just done in the previous page is this relation, and from this we have read off the capacitance of the parallel plate capacitor. What happens to the case if we consider a cylindrical capacitor? Cylindrical capacitor is this one. The red one is charged with positively charged particles, and blue one is a cylinder that is charged with negatively charged particles. Electric field emits from the positively charged particle, and because of the spherical symmetry, and you know how to compute the electric field by making use of Gauss law, and the result was only inside this charge symmetric charge distribution, electric field vanishes. Okay, and outside, because it is a negatively charged minus Q, and here we have plus Q, outside we can introduce a Gaussian surface. If you look at this object, the net charge contained by this Gaussian surface is a 0. So outside electric field is also vanishing. Therefore, electric field is isolated in this region between the radius A and B. In the case of parallel plate capacitor, electric field was constant. However, in this case, electric field decreases by factor of 1 over rho. We know very well, if you have studied the Gauss law and the following computation for the electric field already. But let me repeat that calculation using Gauss law. Electric field flux evaluated over a cylinder. That cylinder is between the radius A and B. This rho is somewhere around here. In that case, electric field is only along the planar radius direction and uniform at given fixed rho. Then, so the electric field area and this area, we unfold this cylinder, and the cylindrical surface reduces to a rectangle of the width is 2 pi rho, and height in here it is L. So this is the area. And electric field is perpendicular to this surface. So simply multiply the electric field and substitute this area. The final result is this one, where lambda is the charge per unit length. As you can see, it is not 1 over r squared, instead 1 over rho, planar radius, rho. And the direction is a planar radial direction, normal direction. Okay. Using this, you can do the integral. 1 over x integral is a logarithm. And the final point, we have chosen the potential V equals 0 at infinity, but outside the electric field is 0. So it is frozen at rho equals B. After that, its potential is fixed. And this range is from A to B. We have a condition. Inside the inner cylinder, it should be frozen. Outside the outer cylinder, potential is also fixed to be a constant value. Using this, we can integrate from this to there, from B to A, where the electric field is present, and this integral becomes just a log of B over A. Now we have found expression Q equals something multiplied by potential. And that something is what? This one's reciprocal. That is this, 2 pi epsilon 0, length divided by log ratio of the two radii. What happens to the case if we introduce a spherical capacitor? Again, in this case, inside the inner sphere, electric field vanishes. Outside the outer sphere, electric field vanishes. only the electric field is present between the two spheres. And the electric field can also be computed by using Gauss law. And let me tell you the final result. It is because you are already well familiar with this is integral. The potential difference is finally obtained like that. Again, Q equals something V, Q equals something V. So reciprocal of this one will be the capacitance of a capacitor constructed by concentric spheres. Parallel connection of capacitors. If you bring many capacitors in parallel, what happens? If you remove this guy, then they were completely discharged. And as soon as you attach the battery in this circuit, electrons will flow to make these charged with appropriate charges, and electrons flow out because they become positively charged. And the Coulomb interaction, they attract together. So electrostatic force makes each plate be charged with opposite direction, opposite charge, but the magnitude should be the same. We can consider an equivalent capacitor. That means it is the same as a single capacitor. So we are interested in simplifying this composite system as a single capacitor. So what is the capacitance of this? That is the question. Anyway, any wire without any element is assumed to have the same electrostatic potential. So from here to there, the potential difference here to there, they must be the same as the potential difference between the two terminals of a battery. So V is constant for everywhere. And we know Q equals CV. That works for every capacitance, every capacitor. So Q1, C1V, and every capacitor has the equal potential difference. So let me use V instead of V1 to Vn. We don't have to distinguish the voltage. And next we consider charge conservation. If there are Q1, Q2 through Qn, then this charge Q must be the sum of the all charges. Using these relations and the fundamental relation, this relation was first obtained by Volta, Alexander Volta, who has actually almost created the capacitor. At least the theory of capacitor was developed by Volta. And we have sum of charges is the net charge. And sum of charge, each charge is a Q equals a CIV, and V is factored out. Oh, we are done. Q equals a something V, then this something is capacitance. This is nothing but the algebraic sum of capacitances of the whole capacitors, if you consider a parallel connection. What happens to the case if you connect them in series? In this situation, because originally they were discharged, if I bring minus Q, electrons flows into minus Q, this guy attracts a plus Q, and in here there were no charge, no net charge. So if you have plus Q in here, the other plate must have equal amount but opposite charge because of the conservation of charge. In series, we can repeat. As a result, all of the charges in all capacitors connected in series must be the same. On the other hand, potential difference must be added up. Now you have Q. This is the same for every case, equals C something times voltage. And VI is like that, charge divided by capacitance. Substitute this one in here. Then what I obtain is, as a common factor, Q is factored out, and the summation is over 1 over capacitance. As a result, you know Q equals something times V, that is a C. Here, what I have computed is a V. V equals 1 over something Q. This something is capacitance. So 1 over capacitance is the sum of reciprocals of the capacitors. All right. Next, we consider electrostatic energy. We know electric field between the two parallel plates. Using this, we obtain the capacitance of a parallel plate capacitor. The work necessary to bring a small amount of charge that is a positive from the negatively charged plate to positively charged plate. Because this is a positive and electric field is this, and you have repulsive force. You have win the game to the repulsive force to bring this charge there. So you need to work that is a positive. And there was a potential difference V, and that is to be computed with Q over C. Q equals CV. Therefore, we have reached a differential relation, the work necessary to bring a positively infinitesimally small positively charged particle from the negatively charged plate to the positively charged plate. You need to work in positive sense. That is very, very similar to x dx. If you pull out the scaling factor physical dimensions, this integral remains. What's that? This one is a universal integral. You know how to compute. This 1 over x, 1/2 x squared appears everywhere when you compute the kinetic energy, when you compute the potential energy due to what? Spring force. Just like that, what you find is 1/2 q squared. And you used to have a c in the denominator. Why don't you replace this one Q with the Q equals the CV? Then it becomes 1/2 CV squared. It's just like 1/2 MV squared, something like that. So mathematical structure is identical. This one we call the electrostatic potential energy. You need to work hard to make these two plates charged. Again, you know the electric field. If you express the potential in terms of electric field, what you obtain is like that. I have made use of these two identities only, and you will find that this is the, what's that? C. And electric field, area, distance squared. And this distance cancels with this d squared, and remove this one, we will find d. What's A times d? This is the area A. This is the distance d. What's that? A times d is the volume inside the parallel plate capacitor. Now you understand this 1/2 epsilon 0 electric field squared multiplied by volume integrated over volume is identical to the electrostatic energy, potential energy. We can interpret this electrostatic energy in terms of the electric field energy saved inside a parallel plate capacitor. It's quite interesting. It is a very, very important. You will find later for the magnetic field energy saved inside a solenoid, and some of them will be the electromagnetic field energy, and that is nothing but the electrostatic energy inside the parallel plate capacitor and the magnetic energy saved inside a solenoid that allows the flow of electric charges. So as the last one, we consider dielectric in a capacitor. Let me tell you very simple idea. We have a parallel plate capacitor whose original electric field is E0. Let me bring in a dipole, and just like you know, we have a magnetic field, so S, N, and S. Two big magnets. Between them, there is a magnetic field. If you put a compass, then what happens? This is attracted by N, and this is S. Something like that. Okay? This is similar dipole structure. So this is we can make electric dipole to align to the electric field, but that is opposite. N attracts S. So this is a positively charged, then electric field is like that, and we have negative, positive, negative, something like that. So alignment is happens inside a parallel plate capacitor. Because of these, the resultant electric field cancels. This cancellation leads to the resultant electric field weaker than before. The reason is that redistribution of alignment of the electric dipole between the two plates opposes the electric field. So if you consider Gaussian surface, usually net charge was there, but redistribution makes the net charge smaller than the previous one. This cancellation leads to cancellation. This is a cancellation. Q is original charge, and Q prime is induced charge due to the alignment of dipole. That is called dielectric. Makes this one is a smaller than Q. That means we can replace this one with Q over kappa, and this is smaller than Q. This is smaller than Q. That means the kappa is greater than 1. We say it is dielectric constant. What happens when we have a kappa is greater than 1? Haha. You know this one very well. Epsilon 0 A over D is the capacitance of a paraplate capacitor. What you have to do is multiplied kappa that is greater than 1. So final result is if you insert the dipole structure that is called the dielectric element such as oil, what you have done is to increase the capacitance. So this is an industrial application of this very elementary concept.